Continuing on in section 8.2 here, we're going to write this polynomial as a product of a polynomial with positive coefficients and a monomial. So again, here we're going to factor it down. 6 is 2 times 3. So I'm going to have 2 times 3. Don't forget that negative is actually a -1 and 4 x's. 18 is going to be 2 times 9, which is 3 times 3. 3 in my 3 column, a 2 in my 2 column. I make an extra 3 column, and don't forget about that -1 and 3 x's. 12, I'm going to factor as 2 times 6, which is 2 times 3. 3 in my 3 column, 2 in my 2 column. I make another column for 2's. Don't forget about our -1 or our x's. Now, when I look for common factors here, I have a common common -1, a common 2, 3, x, and x. Those are our columns that are completely full. So I take -1 times 2 times 3 times x, and that gives me a greatest common factor of -6x squared. Now, we multiply by everything that's left. In my first row, I have x squared left. In my second row, 3 times x, so positive 3x. In my last row, I just have the 2. So here, our polynomial has positive coefficients, and our monomial here, which is also a polynomial, but they wanted a monomial and a polynomial with positive coefficients, and that's what we have here. We can do a real quick double check to make sure these equal each other by distributing back. So -6x to the 4th power, -18x cubed, and -12x squared, which is what we have here. So we are correct. In example 4, we're going to factor a polynomial model. So a helicopter landing pad, or helipad, is sometimes marked with a circle inside a square so that it's visible from the air. What is the area of the red shaded region of the helipad on page 294? Write your answer in standard form. So on 294, they show us that our distance across the top is 2x, which means our radius they give us here, but even if they didn't, we would know that's x because it's halfway across. Our diameter is all the way across, radius is halfway, so half of 2x is x. Now, to find the area of just the shaded region, we're going to take our entire square and subtract out that circle in the middle. So it's going to be the area of our square minus the area of our circle. To find the area of a square, we're going to take our side length and square it. To find our area of a circle, we're going to take our pi times radius squared. So here, my side is 2x. So I'm going to take 2x squared. We also could have thought about this square as a rectangle and done length times width, and we would have gotten to the same spot. My radius is x. I'm going to take that exponent in. Again, when we have a product to a power, we can take that power to each piece, keep it as an exponent, and I have 4x squared minus pi x squared. Now, they want our answer in factored form, though. So I'm going to take my 4 and factor it down as 2 times 2, and then my x squared. My pi times x squared, remember pi is just a number. Not just a number, it's a magical number. But for all intents and purposes here, we're going to put it on our number side. It's got that -1 in front of it, so that's one of our factors as well. X squared means x and x. Our x's here are our common factors. So we take out what's common and we multiply by what's left. In my first row, I have 2 times 2, or 4. In my second row, I have -1 times pi, so minus pi. And this is in units squared. I don't believe they told us anywhere what those are in. And that is our factored form for the area of just the red. Again, we're going to take the entire red square and we're going to subtract out that circle in the middle because that's not shaded in. Now, In example 4, suppose the side length of the square is 6x and the radius of the circle then is 3x. What is the factored form of the area of the shaded region? Feel free to pause here and give this a try again if you'd like. So here it's telling us that our square is 6x, so our radius has to be 3x. We're still going to find the shaded region here, and what the shaded region is, it's the area of our square here, and then they take out the area of that circle. So it's still going to be our side squared minus pi r squared. And our shapes don't have to be these shapes, guys. That's just what we have here again. So if we had a triangle with a circle in it, we'd find the area of our triangle minus the circle. If we had a circle with a square cut out, we'd take our circle minus our square. Whatever our relationship happens to be there. Here we just still have that square and circle. My side length, 6x, and again, I square that. Here my radius is 3x, and I square that. Again, our product to a power says we can take that exponent inside to each piece. 6 squared is 36, x squared. Same thing here, we can take that exponent into both pieces. I get 9 times x squared. I'm just going to rewrite this so it looks a little neater here. But we still want to write it in factored form. So 36 I'm going to break down. 9 times 4, 3 times 3, 2 times 2. And we have x squared with that as well. 9 is 3 times 3, so I'm going to put a 3 in each of my 3 columns. I have a -1, and I have a pi, and I have 2 x's. So my common factors, my x's, I take those out as x squared. Again, that's my greatest common factor. And I also have common 3's here. Sorry. 3 times 3 is 9. So I have 9 x squared as my greatest common factor. We multiply by everything that's left. So if I look here, in my first row, I have a 2 times 2 left, or 4. In my second row, I have pi times -1, or negative pi, minus pi. And this is my area in factored form. So originally there, when I just took out the x's, that was a common factor I could take out, but it wasn't my greatest common factor. And when we factor, we always want to take out the most stuff that we can, that greatest common factor. Real quick recap for 8.2 here. A monomial can be multiplied by a polynomial using the distributive property. Factoring a polynomial reverses the multiplication process. And the first step when factoring a monomial from a polynomial is finding the greatest common factor of the terms of the polynomial. And that's all I have for section 8.2.